Navier Stokes equation. This chapter discusses the Navier Stokes equation as the fundamental basis for analyzing real fluid flows. This equation combines the effects of inertia, pressure, viscosity, and body forces into a single comprehensive formulation. Almost all engineering fluid mechanics problems are rooted in this equation. However, in practice, the full form of the equation is extremely difficult to solve analytically. Therefore, understanding its structure and physical meaning is essential before introducing simplifications.
Lesson Plan: Fluid Mechanics 2. This slide shows the position of the Navier Stokes chapter within the overall structure of the Fluid Mechanics 2 course. After this chapter, the course continues with external flow, compressible flow, open channel flow, and turbomachinery. This sequence indicates that Navier Stokes provides the conceptual foundation for many advanced topics. Mastering this chapter will strongly influence how easily the following chapters are understood. In other words, this is a key chapter in the entire course.
Learning outcome. The learning outcomes emphasize the importance of understanding why approximations are necessary in fluid mechanics. Students are expected to recognize when a flow can be simplified and when the full model must be used. Concepts such as creeping flow, potential flow superposition, and boundary layers become the main focus. All of these aim to make flow analysis efficient while still physically meaningful. In this way, students not only compute results, but also understand the assumptions behind the models.
Motivation: why approximations are needed. Examples such as lava flow or very viscous fluids show that not all flows need to be analyzed using the full equations. In certain conditions, viscous effects dominate far more than inertial effects. In such situations, simplifying the equations actually provides clearer physical insight. Approaches such as creeping flow become highly relevant. This slide emphasizes that model selection must always match the nature of the flow.
Exact versus approximate solutions lies in their complexity and purpose. Exact solutions use the full Navier Stokes equations, but are rarely solvable analytically. Approximate solutions sacrifice some details to obtain practical results. In engineering, this approach is used far more often because it is efficient. The key idea is to choose a model that is sufficiently accurate without making the problem unsolvable.
Flow region approximations. In a single flow system, there are often several regions with different physical characteristics. In one part, the flow may be treated as inviscid, while near the wall, it must be treated as viscous. Between these two regions, there is usually a transition zone. This approach allows different models to be applied in different locations. In this way, the analysis becomes simpler while remaining realistic.
Check your understanding number 1. Approximations change between regions, ensuring accurate predictions of flow behavior. Scaling parameters table. This table introduces scaling parameters used to non-dimensionalize the flow equations. Parameters such as characteristic length, characteristic velocity, and reference pressure difference are essential in non-dimensional analysis. By using these scales, equations can be written in a more general form. This approach also allows comparison between systems of different sizes. This is the basis for dimensionless numbers, such as Reynolds and Froude. Scaling parameters in fluid dynamics. Scaling parameters give physical meaning to the quantities used in flow modeling. The characteristic length represents the system's size, while the characteristic velocity represents the flow intensity. Pressure and gravity determine the main driving forces in the flow. By normalizing the equations using these parameters, the structure of the equations becomes clearer. In addition, the relative importance of each force can be directly seen from the dimensionless numbers.
Gradient operator non-dimensionalization. The gradient operator must also be non-dimensionalized to be consistent with the characteristic length scale. This process can be carried out in both Cartesian and cylindrical coordinates. The result is a form of the equations that does not depend on units or system size. Therefore, one non-dimensional solution can apply to many physical cases. This is one of the main strengths of the non-dimensionalization approach in fluid mechanics.
Dynamic similarity in models. Dynamic similarity between a model and a prototype requires identical geometry and consistent dimensional ratios. In addition, matching dimensionless numbers, such as Reynolds and Froude, is essential to correctly reproduce flow behavior. In practice, satisfying all similarity requirements at once is often difficult. Therefore, engineers usually prioritize the most dominant dimensionless numbers. This approach allows model testing to still provide meaningful information for real systems.
Check your understanding number 2. What is a key requirement for achieving geometric similarity in model testing? B. The model and prototype must have the same shape and proportional dimensions. Explanation of why other answers are wrong. A. The model and prototype must have identical sizes and dimensions. Incorrect, because geometric similarity requires proportional dimensions, not identical sizes. C. Dimensionless parameters like Reynolds and Froude numbers must be mismatched to simplify the test. Incorrect, because matching dimensionless parameters ensures dynamic similarity and accurate test results. D. The prototype must be tested under identical conditions as the model to ensure similarity. Incorrect, because identical conditions are not always feasible. Instead, matching dimensionless parameters and ensuring proportional dimensions achieve similarity.
Pressure distribution in Couette flow. In Couette flow, the difference between modified pressure and actual pressure is important to understand. The modified pressure may remain constant, but the actual pressure varies in the vertical direction due to hydrostatic effects. In other words, the contribution of gravity cannot be neglected in the actual pressure distribution. The boundary conditions at the top or bottom plate determine the shape of the measured pressure profile. This shows that pressure in a flow is not only determined by motion, but also by body forces. Creeping flow characteristics. Creeping flow is a very slow flow in which viscous forces dominate over inertial forces. This condition usually occurs at very low Reynolds numbers. In such situations, acceleration effects have almost no influence on the flow behavior. Everyday examples can be found in the flow of honey or very viscous liquids. The creeping flow approach provides major simplifications in mathematical analysis.
Bacterial interaction and movement is a clear example of flow at the microscale with very low Reynolds numbers. At this scale, motion is entirely controlled by viscous forces rather than inertia. Bacteria use structures such as flagella to generate effective propulsion. This mechanism is very different from how humans swim at the macroscopic scale. This example emphasizes that flow behavior strongly depends on length and velocity scales.
Creeping flow simplification. In creeping flow, the inertial terms in the momentum equation can be completely neglected. As a result, density no longer appears in the equation because viscous forces and pressure gradients become the only controlling factors. The remaining equation becomes much simpler than the full Navier Stokes form. The main balance is between pressure gradient and viscous forces. This simplification is very powerful for analyzing microflows and highly viscous fluids.
Check your understanding number 3. In creeping flow, inertial effects are negligible due to the low Reynolds number. High Reynolds number swimming.
At high Reynolds numbers, inertial forces are much more dominant than viscous forces. Under these conditions, a swimmer can glide a long distance by relying on momentum. Viscous resistance is relatively small compared to the stored kinetic energy. Motion becomes more efficient because continuous propulsion is not required. This example shows a sharp contrast with the microscopic world of creeping flow. Microorganism swimming dynamics. Microorganisms, such as sperm, swim in a regime completely dominated by viscous forces. The wave-like motion of the tail generates propulsion through interaction with the viscous fluid. There is no benefit from inertia, so motion must be continuously maintained. The efficiency of motion is determined by the shape and oscillation pattern of the tail. This again emphasizes that macroscopic mechanical intuition does not apply at the microscale. Movement without inertia. At the microscale, moving in a fluid can be compared to pushing through a dense pile of plastic balls. Once the force is removed, the motion stops immediately because there is no significant inertial effect. All progress in motion depends entirely on the applied force at that moment. This makes movement much more energy-consuming than at large scales. This example reinforces the understanding of viscosity dominance at low Reynolds numbers. Creeping flow drag characteristics. In creeping flow, the drag force does not depend on fluid density, but is entirely governed by viscosity. The magnitude of drag is influenced by the object's size, the relative fluid velocity, and the viscosity. Since the Reynolds number is very small, inertial effects can be neglected completely. This makes the relationship between force and velocity simple and linear. This behavior is very different from flows at high Reynolds numbers. Drag on sphere in creeping flow. For a sphere moving in creeping flow, the drag force follows Stokes' law. The force is proportional to velocity, viscosity, and sphere diameter, with no velocity squared term as in high-speed flows. This linear relationship reflects the complete dominance of viscous forces. With this model, drag calculations become very simple. This law is very important in the analysis of small particles and sedimentation. Check your understanding. Number 4. Under what conditions does Stokes' law accurately describe the drag force on a sphere? C. When the Reynolds number is low and the flow is fully governed by viscous forces. Explanation of why other answers are wrong. A. When the Reynolds number is high and inertial effects dominate. Incorrect because Stokes' law applies in low Reynolds number conditions where inertial effects are negligible. B. When the drag force is independent of the sphere's diameter. Incorrect because Stokes' law states that drag force is directly proportional to the sphere's diameter. D. When the drag force is proportional to the square of the fluid velocity. Incorrect because Stokes' law specifies a linear relationship between drag force and fluid velocity, not a squared relationship. Forces at terminal velocity. At terminal velocity, the net force acting on a particle becomes zero. The weight is balanced by drag and buoyancy forces. Because there is no acceleration, the particle velocity becomes constant. The value of the terminal velocity is determined by particle size, fluid properties, and density difference. This concept is very important in the analysis of particle settling and two-phase flows. Inviscid flow region. At high Reynolds numbers, the effective viscosity becomes very small compared to inertia and pressure gradient forces. In such regions, the flow can be treated as inviscid, even though the fluid is actually viscous. This approach is very useful for analyzing flows far away from walls. By neglecting viscous terms, the equations become much simpler.
However, this approximation is not valid near solid surfaces.
Euler equation application. The Euler equation applies in flow regions where viscous effects can be neglected. This usually occurs in high Reynolds number flows far from walls. Near surfaces, this approximation is no longer valid because friction effects dominate. Nevertheless, the Euler equation is very useful for describing the main flow structure. This approach is often combined with boundary layer theory for real flow analysis. Streamline properties. The gradients of pressure, kinetic energy, and potential energy are always perpendicular to the streamline. Along a single streamline, the sum of P over rho plus V squared over 2 plus GZ remains constant for steady inviscid flow. This is another form of Bernoulli's equation along a streamline. This concept is very helpful for visualizing the relationship between velocity and pressure. In this way, the direction of changes in the flow field can be understood geometrically. Check your understanding. Number 5. The gradient of pressure, velocity, and elevation terms is always perpendicular to the streamline.
Solid body rotation in flow. In solid body rotation, the fluid moves as if it were rotating as a single rigid body. The tangential velocity increases linearly with radial distance from the center. Even though the flow is inviscid, it is rotational. The Bernoulli constant differs between streamlines, but remains constant along each streamline. This model is often used to understand simple rotating flows, such as vortex cores.
Pressure distribution in rotation. In rotational flow, pressure increases non-linearly with radial distance from the center. This pressure rise is caused by centrifugal effects that push the fluid outward. This pressure distribution is very different from that in straight, non-rotating flows. By normalizing the pressure, comparison between different systems becomes easier. This analysis is important for understanding pressure structures in rotating flows.
Irrotational flow approximation is only valid in regions far from rotational effects and vorticity. In these regions, the flow can be treated as having no rotation even though the fluid is real. This simplification allows the use of potential flow models that are much simpler mathematically. However, this approach is not valid near objects or in wake regions. Therefore, its application must always be restricted to appropriate regions.
Proof of vector identity. This vector identity is proven by expanding its form in Cartesian coordinates. Because cross-partial derivatives are symmetric, several terms cancel each other out. The main requirement for this identity to hold is that the function must be continuous and differentiable. Physically, this shows the mathematical consistency of vector differential operations. This result becomes an important basis for simplifying flow equations.
Laplace equation in flow. The Laplace equation applies only in regions where the flow is irrotational. This equation can be used for both two-dimensional and three-dimensional flows. However, it cannot be applied near walls or in wake regions where rotation exists. By using this equation, potential flow analysis becomes much simpler. This makes it a very powerful tool for studying ideal flows.
Check your understanding. 6. Where does the Laplace equation apply in fluid flow analysis? C. In regions where the flow is irrotational, applicable to both two-dimensional and three-dimensional flow fields. Explanation of why other answers are wrong. A. In regions near walls or wake regions where rotational effects dominate, incorrect because the Laplace equation does not apply in rotational flow regions like near walls or wake regions. B. In any flow field, regardless of rotational or irrotational conditions, incorrect because the Laplace equation is specific to irrotational flows and is not valid for rotational flow conditions. D. only in one-dimensional flow fields with uniform velocity profiles. Incorrect because the Laplace equation is versatile and applies to both two-dimensional and three-dimensional flow fields, not just one-dimensional.
Simplification in irrotational flow. In irrotational flow, the three velocity components can be replaced by a single velocity potential function. As a result, the number of equations that must be solved is greatly reduced. This significantly decreases the mathematical workload. This approach is very effective for incompressible and irrotational flows. However, this simplification is only valid as long as the irrotational assumption holds.
Irrotational flow characteristics. Irrotational flow assumes that viscous forces can be neglected compared to inertia and pressure forces. All irrotational flows are inviscid, but not all inviscid flows are irrotational. The fluid itself still has viscosity, but its effects are ignored in the model. This approach aims to simplify analysis, not to change the physical nature of the fluid. Therefore, the limits of the model must always be considered.
Solution steps for irrotational flow. The first step in the analysis is to determine the velocity potential function from the continuity equation. After that, the velocity field is obtained from the gradient of this potential function. Pressure is then calculated using Bernoulli's equation along streamlines. This sequence provides a systematic and efficient procedure. With this approach, many flow problems can be solved analytically.
Flow regions in a tornado. Tornado flow can be divided into two main regions, the core and the outer region. Inside the core, the flow is rotational and is often modeled as solid body rotation. Outside the core, the flow can be treated as irrotational, making it easier to analyze. The boundary between these two regions is located at a certain radius called R. This division helps simplify the overall modeling of tornado flow. Check your understanding number 7. The boundary interface at R equals R separates rotational flow in the core from irrotational flow in the outer region. Far-field boundary conditions. Boundary conditions in regions far away from an object are usually simpler and more stable. The far field is often used to define the flow behavior before it is influenced by the presence of an object. By specifying these conditions, the solution near the object becomes more controlled. This approach is very common in aerodynamics and external flow problems. The far field serves as an important reference for the entire flow field. Pressure continuity in tornado model. In a tornado model, pressure must vary continuously to remain physically consistent. The pressure may have a change in slope with radius, but it cannot jump abruptly. If a sudden pressure jump occurs, the model no longer represents a real flow. Pressure continuity ensures a reasonable force balance in the rotating system. Therefore, selecting an appropriate pressure profile is an important part of tornado modeling. Flow characteristics in tornado center. At the center of a tornado, the pressure reaches its lowest value, driving a strong rotating flow. In this region, the flow is often modeled as solid body rotation. The velocity increases as the distance from the core increases. Centrifugal force becomes the main mechanism that maintains the rotating flow structure. This structure explains why the tornado core is dynamically stable. 2D versus 3D irrotational flow. In two-dimensional flow, a stream function can be clearly defined to describe the flow field. In three-dimensional flow, a stream function cannot be defined in a general way. However, the velocity potential function can still be used for both two-dimensional and three-dimensional flows as long as the flow is irrotational. Both still satisfy the Laplace equation. This difference is important in choosing the appropriate analysis method. Tornado flow analysis.
Tornado flow analysis shows that tangential velocity increases linearly in the core region and decreases in the outer region. Pressure decreases toward the center and reaches a minimum in the core. The boundary at radius r separates these two different flow characteristics. By using non-dimensional forms, velocity and pressure profiles can be compared in a general way. This model provides a simple yet powerful picture of rotating flow structure.
Check your understanding number 8. What happens to the tangential velocity in the outer region, r greater than r, of the flow? C. It decreases non-linearly due to the dominance of centrifugal forces. Explanation of why other answers are wrong. A. It remains constant throughout the outer flow region. Incorrect, because tangential velocity in the outer region does not remain constant. It decreases non-linearly. B. It increases linearly with radius, as in the inner core region. Incorrect, because the linear increase in tangential velocity applies to the inner core, r less than r, not the outer region. D. It reaches a maximum at the boundary interface and then decreases linearly. Incorrect, because the decrease in tangential velocity in the outer region is nonlinear, not linear.
Velocity in two-dimensional flow. In two-dimensional flow, velocity can be decomposed into x and y components. There is no velocity variation in the direction normal to the flow plane. This vector representation simplifies the analysis because only two components need to be considered. Many engineering flow problems can be approached using the two-dimensional assumption. This provides a good balance between simplicity and model accuracy.
Orthogonality in irrotational flow. In irrotational flow, streamlines and equipotential lines are always perpendicular to each other. Streamlines show the direction of fluid particle motion, while equipotential lines represent constant potential values. This orthogonal relationship is a characteristic feature of potential flow. This pattern makes it easier to visualize the structure of the flow field. By looking at one family of lines, the nature of the other can be immediately inferred.
Velocity in cylindrical coordinates. Velocity is decomposed into radial and tangential components. The direction of each component is defined by the unit vectors ER and E theta. This approach is very useful for flows with circular symmetry. With the planar flow assumption, there is no variation along the axis normal to the plane. This coordinate system simplifies the analysis of rotating flows and flows around cylinders.
Flow over axisymmetric body. In axisymmetric flow, the geometry and flow field do not change with the angular coordinate. Under this condition, the angular velocity component becomes zero because there is no tangential variation. The flow depends only on the radial and axial coordinates. This simplification greatly reduces mathematical complexity. This model is widely used to analyze flows in nozzles, bodies of revolution, and pipes.
Check your understanding. Number 9. In rotationally symmetric flow, the angular velocity component, u theta, is zero due to symmetry. Stream function in axisymmetric flow. In axisymmetric flow, a stream function can still be defined, but its governing equation differs from the two-dimensional case. This function is used to represent the flow pattern without an angular component. Even though the flow is irrotational, the governing equation is no longer the simple Laplace equation. This shows that geometric symmetry influences the form of the mathematical equations. This approach is still very useful for visualization and qualitative analysis.
Velocity components overview. Different coordinate systems produce different forms of velocity components. In two-dimensional Cartesian coordinates, velocity components are expressed in the x and y directions. In planar cylindrical coordinates,
components are expressed in the radial and angular directions. For axisymmetric flow, velocity depends only on radial and axial coordinates. This overview helps in choosing the most appropriate formulation for a given flow problem.
Superposition of flow solutions. Superposition allows several irrotational flow solutions to be combined to form more complex flow patterns. This principle works because the governing equations are linear. By adding basic solutions, new flow fields can be constructed without violating the irrotational assumption. This approach is very powerful in potential flow modeling. Many classical flow configurations are built using this principle.
Vector addition in superposition. In superposition, the total velocity vector at a point is obtained by adding the velocity vectors of all component flows. Each component contributes a certain magnitude and direction. The resulting sum represents the actual flow behavior at that point. This approach is very intuitive because it follows standard vector addition rules. In this way, the effects of multiple flow sources can be analyzed simultaneously.
Check your understanding number 1. What does the resultant velocity vector represent in the superposition of velocity components? The correct answer is B, temperature difference across the P and N-type materials.
Building complex flow fields. Complex flow fields can be constructed from simple flow elements, such as uniform flow, sources, sinks, and vortices. Each element serves as a basic building block. By combining them using the superposition principle, realistic flow patterns can be modeled. This approach provides great flexibility in analysis and design. Many classical solutions in aerodynamics are built in this way. Uniform stream flow characteristics. In uniform flow, the velocity is constant and its direction is parallel throughout the domain. The streamlines are straight, parallel lines with equal spacing. Equipotential lines are always perpendicular to the streamlines. This pattern reflects a very simple and orderly flow field. Although simple, this flow is often used as a basic component in superposition.
Inclined uniform stream flow. If a uniform flow is inclined with respect to the x-axis, the streamline pattern remains straight lines, but at a certain angle. The velocity components in the x and y directions change according to the inclination angle. Equipotential lines remain perpendicular to the streamlines. Physically, this is still a uniform flow, only its orientation has changed. This example shows that the coordinate system can be chosen flexibly.
Line source. A line source represents flow that emerges radially from a line in all directions within a plane. If the length of the source segment is extended to infinity, the flow approaches the behavior of a continuous line source. The flow field is usually analyzed in a plane normal to the source axis. This model is very useful for understanding symmetrically spreading flows. This element is also often used as a component in more complex superposed flows.
Check your understanding number 11. As the segment length extends to infinity, the flow approximates a continuous line source.
Characteristics of line source flow. Flow from a line source spreads radially outward in all directions within the plane. The volumetric flow rate per unit depth remains constant for any circle of any radius. This means the source strength does not change with distance. The velocity distribution changes only because the effective flow area increases. This model provides an ideal example of flow rate conservation in two-dimensional flow. The flow pattern of a line source is shown by streamlines radiating outward from the center. The equipotential lines form concentric circles that are always perpendicular to the streamlines. This pattern shows perfect radial symmetry. By looking at this figure, the relationship between the potential function and the stream function becomes very clear. This representation is often used as a basic reference in potential flow. If a line source is placed at an arbitrary location, the flow pattern remains the same, but the center of symmetry shifts. Any point in the flow field can be analyzed based on its distance and angle relative to the source position. Mathematically, this only requires a change in the coordinate system. Physically, the flow behavior does not change. This approach makes it easier to model multiple sources at different locations.
Superposition of line source and sink. The combination of one source and one sink produces a distinctive and symmetric flow pattern. Streamlines emerge from the source and enter the sink. This pattern shows how fluid is transported from one location to another without mass accumulation. By the superposition principle, the total velocity field is obtained by adding the two fields. This configuration is often used as a basis for building more complex flow models.
Check your understanding number 12. Streamlines diverge from the source and converge at the sink, maintaining radial flow. Trigonometric identity highlights. Trigonometric identities are used to simplify angular expressions in flow analysis. Relationships between sine, cosine, tangent, and cotangent often appear in coordinate transformations. By using these identities, equation forms can be made more compact and easier to manipulate. Although purely mathematical, their role is very important in simplifying solutions. Without these tools, many analytical solutions would become very complicated. Line vortex properties. A line vortex represents rotating flow around a central point. The flow velocity is tangential and inversely proportional to the radial distance from the center. This model is an idealization of a vortex without a viscous core. Although simple, this model is very useful in aerodynamics and potential flow theory. Many complex rotating flows can be understood as combinations of several ideal vortices. Arbitrary line vortex. If a line vortex is placed at an arbitrary location, the velocity field throughout the domain is affected. The velocity at a point is determined by its distance and orientation relative to the vortex. Mathematically, the equation form is similar to the centered vortex case, only with shifted coordinates. Physically, there is no change in the fundamental nature of the flow. This allows modeling of multiple vortices in one system. Induced velocity components. A vortex induces a tangential velocity component around it, while a source induces an outward radial velocity component. A sink induces an inward radial component. At a point, all these components are added vectorially to obtain the total velocity. This approach shows how different flow elements influence the velocity field simultaneously. This is the basis for constructing complex flow fields through superposition.
Doublet flow characteristics. A doublet is formed by combining a source and a sink with very large strengths and very small separation distance. Even though the distance shrinks, the product of strength and distance remains constant and defines the doublet intensity. The resulting flow field has a symmetric pattern with radial and angular components. This model is often used as a basic element in constructing flow around bodies. Physically, the doublet helps represent local disturbance effects in potential flow. Check your understanding number 13. What defines the intensity of a doublet in fluid mechanics? B. The product of the source strength and the separation distance, which remains constant. Explanation of why other answers are wrong. A. The separation distance between the source and sink, independent of their strengths. Incorrect,
because the intensity of the doublet depends on both the strength of the source and the separation distance, not just the distance. C. The sum of the source and sink strengths divided by their separation distance. Incorrect, because the doublet's intensity is defined by the product of the source strength and the distance, not their sum divided by the separation. D. The ratio of the angular velocity to the radial velocity of the induced flow field. Incorrect, because the doublet's intensity is not defined by velocity ratios, but by the source strength and separation distance.
Flow field of a doublet. The flow pattern of a doublet is shown by streamlines that are symmetric about a certain axis. The equipotential lines are always perpendicular to the streamlines, showing the nature of potential flow. This pattern reflects the combined influence of a source and a sink placed very close together. Although idealized, this structure is very important as a building block for flow around bodies. From this pattern, flow behavior near obstacles can be understood qualitatively.
Superposition of source and vortex. If a source is combined with a vortex, the resulting flow pattern becomes a spiral. The flow has a radial component due to the source and a tangential component due to the vortex. At each point, the total velocity is obtained by vectorially adding these two effects. This pattern is often used to model rotating flows that also spread outward. Visually, it shows how rotation and radial motion can occur simultaneously.
Streamlines of sink and vortex. The combination of a sink and a vortex produce spiral-shaped streamlines that move toward the center. The fluid not only rotates, but also moves inward toward the core. The stream function values indicate the flow intensity on each line. This pattern is often used to model flows such as water swirling into a drain. This structure gives an intuitive picture of rotating flows with suction.
Superposition of uniform stream and doublet. When a uniform flow is combined with a doublet, the resulting flow field becomes more complex and interesting. The velocity at each point is obtained from the vector sum of the uniform flow and the doublet flow. This interaction produces a characteristic streamline pattern around the doublet center. This configuration becomes the basis for modeling flow around bluff bodies. From here, the concept of flow around a cylinder can be developed.
Streamline formation in superposition. The superposition of a uniform flow and a doublet can produce a closed circular streamline. This streamline represents an imaginary boundary that the flow cannot cross. Mathematically, this line is a location where the stream function has a constant value. Physically, this line can be interpreted as the surface of a body. This concept is very important in modeling flow around solid objects. Check your understanding. Number 14. The combination of a uniform stream and a doublet creates a circular streamline. Streamlines from superposition. By choosing appropriate parameters, the superposition of a uniform flow and a doublet can produce a streamline pattern that resembles a cylinder. A particular streamline acts as the boundary of the cylinder surface. The flow then deflects symmetrically around this boundary. Even though there is no real object, the flow field behaves as if a solid cylinder were present. This shows the power of potential flow methods in conceptual modeling.
Flow over a circular cylinder. Flow around a circular cylinder can be analyzed using a potential flow model obtained from superposition. The flow splits symmetrically in front of the cylinder and recombines behind it. The angular position around the cylinder is used to describe the velocity and pressure distribution. This model provides an ideal picture without viscosity and separation effects. Although idealized, it is very useful as a first reference before considering boundary layer effects.
Static pressure measurement? Static pressure on a body surface is measured using pressure taps connected to measuring devices. The measured pressure represents the local pressure acting normal to the surface. Instruments such as manometers or pressure transducers are used to obtain this data. This pressure distribution is very important for calculating aerodynamic forces. From this, the relationship between flow patterns and forces on the body can be understood.
Pressure coefficient distribution. The pressure coefficient is used to present pressure distribution in a non-dimensional form. Its value changes with the angular position around the cylinder. Experimental results show clear differences between laminar and turbulent flows, especially regarding separation points. The ideal irrotational flow curve often deviates from real data because of boundary layer effects. This comparison shows the importance of viscosity in real flows.
Check your understanding number 15. What causes deviations between the idealized irrotational flow and experimental results around a circular cylinder? B. Boundary layer effects, including laminar and turbulent separation, which are not accounted for in the idealized model. Explanation of why other answers are wrong. A. Differences in fluid density across the cylinder's surface. Incorrect, because the density is generally assumed constant in both the idealized and experimental models for incompressible flow.
Aerodynamic drag and flow fields. In ideal irrotational flow, the aerodynamic drag is predicted to be zero. However, in real flows, the presence of wake and separation causes the drag to be non-zero. This difference is known as D'Alembert's paradox. This paradox shows the limitation of purely potential flow models. Therefore, viscous effects must be considered to predict forces realistically. Fish body design and pressure distribution. The shape of a fish body is designed to minimize unfavorable pressure variations. The fish's eyes are located near a zero pressure region to avoid visual distortion. The pressure profile along the body helps maintain stability and swimming efficiency. This example shows how nature optimizes the interaction between shape and flow. The same principles are often adopted in vehicle and ship design. Flow over a symmetric hill. In this model, a particular streamline is treated as a solid wall, representing a symmetric hill. The flow smoothly deflects, following the hill contour without separation in the ideal model. This approach is used to study the influence of topography on airflow. Although idealized, this model provides initial insight into terrain aerodynamics. It also shows the flexibility of potential flow methods in modeling complex geometries. Vacuum cleaner flow. The flow in a vacuum cleaner can be modeled using the line sink concept. The device geometry is shown in one plane, while the suction effect is represented in another plane. This model helps to understand how air flows into the nozzle. With this approach, velocity and pressure distributions can be estimated qualitatively. This example shows the application of potential flow concepts to everyday devices.
Superposition of line sources. Two line sources placed symmetrically about an axis produce a symmetric flow field. In this configuration, the axis of symmetry acts as a streamline. This means no flow crosses that line. Such models are often used to represent wall or floor effects using the method of images. This approach is very useful in many near-boundary flow problems.
Check your understanding number 16. The x-axis acts as a streamline due to the symmetric flow distribution created by two mirror sources. Dividing streamline.
The axis line in the two-source configuration acts as a dividing streamline that separates two flow regions. Fluid from one source will not cross into the region influenced by the other source. This creates a natural boundary in the flow field. The concept of a dividing streamline is very important for understanding flow domain separation. By observing this line, the global flow structure can be immediately understood.
Streamlines towards sinks. If both sources are replaced by sinks, all streamlines will be directed toward the sink locations. The flow pattern remains symmetric, but the flow direction is reversed compared to the source case. Fluid from the entire domain is drawn toward the sinks. This model can be used to represent suction or mass removal processes. Visually, it provides a clear picture of a converging flow field.
Symmetry in induced velocities. The velocity at a point is obtained from the vector sum of velocities induced by each sink. Due to symmetry, at certain axes, the vertical components cancel each other. As a result, the total velocity has only a horizontal component. This phenomenon shows how geometric symmetry simplifies the flow field. Such analysis is often used to verify solution consistency. Axial velocity and pressure profile. The axial velocity profile along the floor shows variations due to the interaction between suction and the solid boundary. At the same time, the pressure coefficient indicates regions of lower pressure beneath the nozzle. This relationship shows how flow acceleration is directly related to pressure reduction. This pattern is important for understanding vacuum device performance. From this graph, force and flow distributions can be analyzed qualitatively.
Check your understanding number 17. What does the green curve in the described flow dynamics represent? B. Changes in pressure coefficient below the vacuum, indicating suction effects. Explanation of why other answers are wrong. A. Fluctuations in axial velocity along the normalized floor distance. Incorrect, because the axial velocity is represented by the blue curve, not the green curve. C. The alternating peaks of velocity caused by the interaction between suction and the floor. Incorrect, because the green curve represents pressure coefficient changes, not velocity peaks. D. The relationship between flow temperature and normalized distance from the floor. Incorrect, because temperature is not mentioned or relevant in the described flow dynamics. The focus is on velocity and pressure. The maximum speed along the floor occurs at certain locations that are not directly beneath the nozzle center. Directly under the nozzle center, there is a stagnation point where the velocity becomes zero. The flow pattern is symmetric about the center line. The nozzle width and suction strength strongly influence the shape of the velocity distribution. This information is important for optimizing vacuum device design.
Boundary layer approximation. The Euler equations allow slip at walls, while the Navier Stokes equations impose a no-slip condition. This difference creates a conceptual gap in modeling real flows. The boundary layer approximation bridges these two models. By dividing the flow into an outer inviscid region and a thin viscous layer near the wall, the analysis becomes more realistic. This concept is one of the main pillars of modern fluid mechanics.
Prandtl's boundary layer concept. According to Prandtl, the flow can be divided into two main parts, the outer flow and the boundary layer. Inside the boundary layer, viscous effects are very dominant. Outside the boundary layer, the flow is almost unaffected by viscosity. This division allows major simplifications in solving flow equations. This concept forms the basis of almost all practical aerodynamic analysis.
Boundary layer characteristics with Reynolds number. As the Reynolds number increases, the boundary layer becomes thinner. This happens because inertial forces become more dominant compared to viscous forces. The boundary layer thickness also changes along the flow direction. These changes influence friction forces and the potential for separation. Therefore, the Reynolds number is a key parameter in boundary layer analysis.
Laminar boundary layer visualization. The visualization of a laminar boundary layer shows how the layer thickness increases along a flat plate. The tellurium method is used to make the flow profile visible experimentally. The steepest velocity gradient occurs near the wall. This pattern shows the gradual transition from zero velocity at the wall to the free stream velocity. This image is very helpful for building intuition about boundary layer structure.
Check your understanding. Number 18. The boundary layer profile is captured using the tellurium method, showing laminar flow development over the flat plate. Boundary layer applications in flow regions. Boundary layers do not only appear over flat plates, but also in jets, wakes, and mixing layers. In jets, the boundary layer forms between the fast stream and the surrounding quiescent fluid. In wakes, this layer appears due to flow deceleration behind a body. In mixing layers, the boundary layer develops between two parallel streams with different velocities. All these cases show that viscosity always creates a velocity transition zone.
Streamlines and boundary layer insights. Streamlines outside the boundary layer are nearly parallel to the surface, but they begin to curve near the separation region. The boundary layer thickness increases along the flow direction. The velocity profile shows a very steep gradient near the wall due to viscosity. Streamlines can cross the boundary layer curve because the boundary layer is not a particle path, but a velocity-based definition. This helps distinguish between geometric and physical concepts in flow visualization.
Transition of boundary layers. The boundary layer is initially laminar near the leading edge. As distance and local Reynolds number increase, small disturbances begin to grow. This region is called the transition region. After that, the flow becomes turbulent with much stronger mixing. This transition strongly affects friction and drag characteristics.
Boundary layer thickness progression. Boundary layer thickness increases from the laminar region toward the turbulent region. A smooth wall and calm free stream conditions help maintain laminar flow longer. After disturbances grow, the boundary layer enters the transition phase. In the turbulent region, thickness increases more rapidly and mixing becomes stronger. These changes strongly affect friction and heat transfer.
Check your understanding number 19. What characterizes the transition from laminar to turbulent flow in a boundary layer? B. Unstable disturbances grow in the transitional region, leading to increased mixing and chaotic flow in the turbulent region. Explanation of why other answers are wrong. A. The boundary layer becomes thinner and less chaotic due to reduced energy dissipation. Incorrect, because in turbulent flow, the boundary layer becomes thicker and more chaotic, with increased energy dissipation. C. The boundary layer maintains its laminar characteristics, but grows thicker as it progresses downstream. Incorrect, because the laminar flow does not persist indefinitely. It transitions to turbulence through the unstable transitional region. D. The boundary layer immediately transitions to turbulence with no intermediate region of instability. Incorrect, because there is always a transitional region where disturbances grow before fully developing into turbulent flow. Tripwire and transition dynamics. A tripwire is used to trigger an earlier transition from laminar to turbulent flow. By introducing artificial disturbances, the boundary layer becomes unstable more quickly. This is often done in experiments to control the transition location. A turbulent boundary layer has stronger mixing and higher friction.
This example shows that surface conditions strongly influence flow behavior.
Boundary layer growth on fin surface. The boundary layer develops along the fin surface due to viscous effects in the fluid. Its thickness increases from the leading edge toward the trailing edge. This change modifies the flow pattern around the fin and affects drag and lift forces. The interaction between the main flow and the viscous layer determines the aerodynamic performance of the fin. Therefore, fin geometry plays a crucial role in controlling boundary layer development.
Boundary layer coordinate system. The boundary layer coordinate system is defined with the x-axis along the surface and the y-axis normal to the surface. The origin is usually placed at the stagnation point in front of the body. With this definition, velocity variations along and across the boundary layer can be analyzed clearly. This approach simplifies the formulation of equations and their physical interpretation. This coordinate system becomes the standard in almost all boundary layer analyses.
Boundary layer characteristics. The boundary layer thickness increases along the surface, usually denoted by delta. Inside this layer, velocity changes from 0 at the wall to nearly the free stream velocity at the edge. The largest velocity gradient occurs near the wall. This shows the dominance of viscous effects close to the surface. This structure is a fundamental feature of all flows with boundary layers.
Velocity components in boundary layer. Inside the boundary layer, the tangential velocity component is much larger than the normal component. The tangential velocity increases from 0 at the wall to the free stream velocity at the layer edge. The normal component remains small, but is necessary to satisfy mass continuity. The difference in scale between these two components forms the basis of boundary layer equation simplifications. This explains why the flow is highly directed near the wall. Check your understanding. Number 20. The tangential velocity component increases from 0 at the wall to match the free stream velocity at the outer edge of the boundary layer. Pressure distribution in boundary layer. Pressure varies significantly along the flow direction within the boundary layer. However, in the direction normal to the wall, the pressure is almost constant. The pressure inside the boundary layer is determined by the outer flow. This shows that the boundary layer adjusts itself to the external pressure conditions. This concept is very important in the analysis of flow separation.
Static pressure measurement. Static pressure is measured using pressure taps installed on the wall surface. These taps usually measure the outer flow pressure rather than the pressure inside the boundary layer itself. This data is used as input for boundary layer analysis. In this way, the relationship between the outer flow and near-wall flow can be studied. This measurement is very important in aerodynamic experiments.
Boundary layer growth. On a flat plate, the laminar boundary layer thickness increases gradually along the flow direction. The outer flow velocity remains constant, while inside the boundary layer, the velocity changes with distance from the wall. This thickness growth is proportional to the square root of the distance along the plate. This relationship shows the diffusive nature of viscous effects. This pattern forms the basis of the Blasius solution.
Outer flow and pressure relation. The outer flow velocity can change along the wall due to pressure distribution. This change influences boundary layer development through momentum transfer mechanisms. In other words, the boundary layer always adapts to the outer flow conditions. This relationship is very important in flows with pressure gradients. An adverse pressure gradient can trigger flow separation.
Boundary layer flow conditions. Boundary layer equations are parabolic in nature and therefore require boundary conditions only on three sides of the domain. No boundary condition is needed at the downstream edge because the solution marches in the flow direction. Initial conditions are specified at the wall and at the flow inlet. This property makes boundary layer computations more efficient. However, this assumption is only valid as long as separation does not occur. Check your understanding number 21. Why are no boundary conditions required at the downstream edge of the flow domain in boundary layer equations? B. The parabolic nature of boundary layer equations allows the solution to propagate downstream without needing conditions at the edge. Explaining why other answers are wrong. A. The downstream edge is influenced entirely by the tangential velocity component and does not require additional conditions. Incorrect because while tangential velocity is important, the lack of boundary conditions is due to the parabolic nature of the equations, not just velocity considerations. C. Boundary conditions are already defined at the upstream edge and wall, making the downstream edge irrelevant. Incorrect because the downstream edge is not irrelevant. It's the parabolic nature that eliminates the need for boundary conditions there. D. The downstream edge is assumed to have uniform pressure, eliminating the need for velocity conditions. Incorrect because pressure uniformity is not the reason. The equations inherently allow for downstream propagation without needing additional conditions. Boundary layer procedure overview. The boundary layer analysis procedure starts by determining the external flow conditions as the main input for the calculation. Then, the boundary layer is assumed to be very thin compared to the body dimensions so that the equations can be simplified. With this assumption, the boundary layer equations can be solved to obtain the velocity profile and other key parameters. The results are then used to compute quantities such as boundary layer thickness and friction force. The final step is to verify whether the thin layer assumption remains valid for the analyzed condition.
Curvature effects on boundary layer thickness. The thin boundary layer assumption begins to fail when the wall curvature is of the same order as the boundary layer thickness. On curved surfaces, centripetal acceleration becomes significant and can no longer be neglected. This condition introduces a noticeable pressure gradient across the boundary layer. As a result, pressure is no longer constant across the layer, violating the basic boundary layer assumption. Therefore, this approximation must be used carefully for strongly curved geometries.
Flow setup for semi-infinite plate. The analyzed system is a uniform flow over a very long flat plate that can be considered semi-infinite. The fluid flows parallel to the plate surface and forms a boundary layer due to viscous effects. Outside the boundary layer, the flow remains uniform and unaffected by the plate. The key parameters involved are the fluid density, dynamic viscosity, and kinematic viscosity. This configuration serves as the classical basis for laminar boundary layer analysis. Outer flow characteristics. The outer flow velocity is assumed to be constant and parallel to the flat plate along the flow direction. The x-axis is aligned with the main streamline to simplify the mathematical formulation. Since there is no variation in velocity or pressure in the outer flow, this condition is referred to as a trivial outer flow. Therefore, all the complexity of the problem appears only inside the boundary layer. This simplification allows the analysis to focus on viscous effects near the wall. Check your understanding number 22. The outer flow velocity remains constant and parallel to the flat plate. Boundary layer features. The very thin boundary layer has a negligible influence on the outer flow dynamics. In illustrations, the boundary layer thickness is often exaggerated to make it visible. Physically, however, the outer flow velocity remains constant and is not affected by the presence of this thin layer.
This confirms that the main interaction between viscosity and inertia occurs only near the wall. Therefore, the boundary layer approach clearly separates the flow regions.
Similarity in boundary layer. Boundary layer flow exhibits geometric similarity, meaning the shape of the velocity profile remains similar even when the scale changes. From a distant view, the layer appears as a smooth, thin film over the surface. However, when observed closely, the velocity variation inside the layer becomes very clear. This concept helps explain why a single solution can represent many flow conditions. This is the basis for using similarity variables in boundary layer theory. Blasius boundary layer profile. The Blasius profile defines the boundary layer thickness as the location where the velocity reaches 99% of the free stream velocity. This profile shows a very steep velocity gradient near the wall and becomes flatter away from the wall. A similarity variable is used to combine the effects of the streamwise distance and the normal distance from the wall. This solution applies to laminar flow over a flat plate with constant outer flow. The profile is a classical reference in boundary layer studies.
Boundary layer on a car hood. Airflow over a car hood forms a boundary layer due to friction with the curved surface. The flow velocity increases with the distance from the surface until it approaches the free stream velocity. In the figure, the boundary layer thickness is exaggerated to make the structure visible. Physically, this layer remains thin compared to the size of the car geometry. This example shows that the boundary layer concept also applies to curved surfaces.
Blasius laminar boundary layer insights.
The Blasius analysis introduces a similarity variable, eta, that combines the streamwise and wall normal coordinates into a single parameter. The stream function f increases with eta and represents the development of the flow inside the boundary layer. The second derivative, f prime prime, is directly related to the wall shear stress, which decreases as the distance from the wall increases. The first derivative, f prime, represents the velocity profile that asymptotically approaches the free stream velocity. This solution is obtained numerically, for example using the Runge-Kutta method, since no closed-form analytical solution exists.
Check your understanding number 23. What does f prime represent in the context of the boundary layer structure? B. The velocity profile within the boundary layer structure, normalized by the free stream velocity. Explanation of why other answers are wrong. A. The boundary layer thickness at a specific streamwise distance, incorrect because f prime represents the velocity profile, not the boundary layer thickness. C. The shear stress at the wall, indicating how friction affects the flow. Incorrect because f double prime, not f prime, corresponds to the shear stress at the wall. D. The rate of increase of the stream function with respect to the similarity variable. Incorrect because while f prime is derived from the stream function, it specifically represents the normalized velocity profile, not just the rate of increase. Wall shear stress behavior. The wall shear stress decreases as the distance from the leading edge of the plate increases. This happens because the velocity gradient near the wall becomes smaller as the boundary layer grows thicker. As a result, the skin friction per unit area is highest near the front part of the plate. This distribution explains why the largest contribution to drag comes from the leading portion of the surface. In practice, this is important for surface design to control skin friction. Displacement thickness concept. The displacement thickness represents an apparent outward shift of the wall caused by the reduced velocity near the surface. Physically, it represents the reduction in mass flow rate due to the presence of the boundary layer. The outer flow feels this effect as if the body's surface were thicker.
This concept allows the effect of the boundary layer to be incorporated into an ideal outer flow analysis. In this way, the interaction between viscous and inviscid flows can be modeled in a simple manner.
Displacement thickness. In laminar flow over a flat plate, the displacement thickness is approximately 1/3 of the 99% boundary layer thickness. This value provides a quantitative measure of how strong the boundary layer influences the outer flow field. The thicker the boundary layer, the larger the displacement thickness becomes. This concept is important in continuity calculations and in predicting changes in the external flow field. In other words, displacement thickness links the real flow to the idealized model.
Check your understanding. Number 24. Displacement thickness quantifies the reduced flow area caused by the boundary layer, affecting flow continuity and drag calculations.
Apparent wall effect. Because of the boundary layer, the wall effectively appears thicker to the outer flow. This causes the actual outer flow velocity to differ from the original assumption without a boundary layer. By accounting for the displacement thickness, this effect can be incorporated into the outer flow model. This approach is very important in drag and pressure distribution calculations. Conceptually, the boundary layer modifies the effective geometry of the body seen by the flow.
Boundary layer growth in a channel. In a channel, boundary layers grow from both the top and bottom walls and gradually reduce the core flow area. Because of this reduction, the core flow accelerates to satisfy the continuity equation. The velocity profile changes from nearly uniform to increasingly curved and eventually approaches a parabolic shape. The displacement thickness from both sides plays a major role in this process. The interaction of the two boundary layers strongly influences the overall flow characteristics in the channel.
Diverging test section walls. To keep the core flow velocity uniform, the test section walls are designed to diverge slightly in the flow direction. This divergence compensates for the reduction in effective cross-sectional area caused by the growth of displacement thickness. With this design, the acceleration of the core flow can be avoided and uniform flow conditions can be maintained. This approach is very important in wind tunnel experiments and aerodynamic testing. In practice, it significantly improves the accuracy of measurements.
Check your understanding number 25. Why is a diverging test section used in experimental setups involving boundary layers? B. To compensate for the displacement thickness by increasing the cross-sectional area, maintaining uniform core flow velocity. Explanation of why other answers are wrong. A. To decrease the displacement thickness and reduce boundary layer effects on the outer flow. Incorrect, because the diverging section does not reduce displacement thickness. It compensates for it to maintain uniform velocity. C. To accelerate the core flow further by narrowing the cross-sectional area and reducing velocity variations. Incorrect, because the diverging test section increases the cross-sectional area, not narrows it, to prevent unwanted acceleration. D. To eliminate the boundary layer entirely, ensuring the flow behaves as an ideal fluid. Incorrect, because boundary layers cannot be entirely eliminated. The diverging section manages their effects on core flow.
Control volume analysis. The control volume boundaries are shown by dashed lines that include the plate and an outer streamline. The main force acting on the system is the viscous shear force from the plate. The outer streamline is assumed to be unaffected by the boundary layer thickness. This assumption simplifies the analysis because the outer flow can be treated as a reference. As a result, the calculation focuses on the changes caused by the boundary layer thickness. Mass conservation in boundary layers. The boundary layer causes a deficit in mass flow rate compared to the free stream. This deficit can be represented as an area under the velocity deficit curve. That area is equivalent to a chunk of free stream flow
that is effectively displaced by the boundary layer. This concept leads directly to the definition of displacement thickness. In this way, mass conservation is satisfied, even though the velocity profile is non-uniform.
Key insights on boundary layer thickness. Displacement thickness represents the thickness of an equivalent layer, accounting for the reduction in mass flow rate due to the boundary layer. For laminar flow, it is about 35% of the 99% boundary layer thickness. Momentum thickness describes the reduction in momentum flux and is about 13.5% of the boundary layer thickness. These parameters show that the boundary layer effect is not only local near the wall. They are essential in analyzing drag and momentum changes in the flow.
Check your understanding number 26. Momentum thickness quantifies the reduction in momentum flux caused by the presence of the boundary layer.
Characteristics of turbulent boundary layer. The turbulent boundary layer is characterized by a time-averaged velocity profile that represents fluctuating flow in a statistically smoothed sense. The thick line shows the mean profile, while the boundary indicates where velocity approaches the free stream value. The turbulent layer is much thicker than the laminar one. Strong momentum mixing makes the near-wall velocity gradient steeper. These features explain why turbulence increases friction and energy losses. Comparison of laminar and turbulent profiles. The laminar profile shows a smooth and gradual increase of velocity from the wall. The turbulent profile rises much more steeply near the wall due to strong mixing. As a result, the turbulent boundary layer is thicker than the laminar one. At the same distance from the wall, turbulent flow has higher momentum. This difference is crucial in analyzing skin friction and momentum transfer. Physical profiles at the same x location. At the same x location, the turbulent profile is always thicker than the laminar profile. Intense mixing in turbulent flow transports momentum from the outer region toward the wall. This causes higher near-wall velocity compared to the laminar case. In contrast, laminar flow has a smoother and more orderly profile. Consequently, energy dissipation in turbulent flow is much larger.
Laminar versus turbulent boundary layers. Laminar boundary layers grow more slowly than turbulent boundary layers. The momentum thickness is always smaller than the displacement thickness in both laminar and turbulent flows. In turbulent flow, the local skin friction coefficient is higher due to strong mixing. This means surface friction drag is higher in turbulent flow. This difference is critical in engineering drag calculations.
Turbulent profile comparisons. The 1/7 power law provides a simple approximation for turbulent velocity profiles, but is inaccurate near the wall. The logarithmic law gives a better description in the near-wall region. Spaulding's law combines near-wall and outer region behavior more consistently. This approach bridges the two different flow regions. As a result, turbulent profiles can be modeled more realistically.
This question emphasizes the importance of selecting the correct velocity distribution law for turbulent flow. The main focus is on a model that can represent both the near wall and outer regions simultaneously. Spaulding's law is chosen because it combines the two main approaches. This shows that simple approximations are not always sufficient for detailed analysis. The choice of model strongly affects friction prediction accuracy. The correct answer is C, Spaulding's law, which combines near wall and outer region behavior, bridging power and log laws effectively. Explanation of why other answers are wrong. A, 7th power law, which approximates velocity distribution throughout the boundary layer. Incorrect, because the 7th power law is a simplification for turbulent regions and diverges near the wall, not effectively bridging the entire boundary layer. B, logarithmic law,
which provides accurate behavior near the wall but fails in the outer region. Incorrect, because while the logarithmic law is accurate for near-wall behavior, it does not capture outer region flow dynamics as effectively as Spaulding's law. D. Linear law, which applies only to laminar flows with constant gradients. Incorrect, because the linear law is irrelevant for turbulent flows, which exhibit complex velocity distributions.
Turbulent flow profile comparisons. Turbulent flow profiles are described using several approaches, from the viscous sublayer to the wake region. The relation U plus equals Y plus is used very close to the wall, where viscous effects dominate. The 1/7 power law provides a simple approximation, but becomes inaccurate far from the wall. The logarithmic law and Spaulding's law improve predictions over a wider range. The wall-wake law gives the best agreement with experimental data over most of the layer.
Boundary layer in flows. Boundary layers appear in both external and internal flows. On an aircraft, the boundary layer along the fuselage influences drag and wake structure. In a diffuser, the boundary layer on the wall affects pressure recovery and flow uniformity. Non-zero pressure gradients modify the growth rate of the boundary layer. This shows that geometry and flow conditions strongly control system performance.
Pressure gradients in boundary layers. A favorable pressure gradient occurs when pressure decreases in the flow direction. This condition helps the boundary layer remain attached and develop smoothly. In contrast, an adverse pressure gradient appears when pressure increases along the flow. This opposes the near-wall motion and can trigger separation. The transition between these two conditions strongly controls drag and flow stability.
Boundary layer separation. At moderate angles of attack, an adverse pressure gradient can start causing partial separation. At high angles or stall conditions, separation becomes extensive and the flow turns highly unsteady. This leads to a strong loss of lift and a large increase in drag. The wide-angle diffuser case shows that separation also reduces efficiency in internal flows. Therefore, separation is a critical phenomenon that must be avoided in design. Check your understanding. Number 28. At a high angle of attack, or stall, significant flow separation leads to a loss of lift and an increase in drag. Boundary layer profiles and pressure gradients. The boundary layer behavior is strongly influenced by the pressure gradient along the surface. Under a favorable pressure gradient, the flow accelerates and the velocity profile remains attached to the wall with positive shear stress. For zero and mild adverse gradients, the flow starts to decelerate near the wall and the shear stress decreases. When the gradient becomes critical or strongly adverse, the flow can no longer overcome the pressure rise and separation occurs. This phenomenon is fundamental to understanding performance losses in wings or diffusers. Flow over a bump. This figure shows how streamlines change when the flow passes over a bump-shaped surface. On the front side of the bump, a favorable gradient makes the flow more compact and organized. After the crest, the pressure gradient becomes adverse, and the flow starts to weaken. Under certain conditions, the streamlines indicate the onset of separation. This visualization helps explain the relationship between geometry and flow stability. Flow over a two-dimensional bump shows regions of favorable and adverse pressure gradients. Downstream, the laminar flow can separate and form a recirculating separation bubble. The separation point is identified by the appearance of reverse flow near the wall. The dividing streamline separates the main flow from the trapped recirculating flow. A comparison with the Euler solution shows that without viscosity, separation cannot be predicted. Experimental visualization of separation. These experimental photographs show different flow patterns around sharp corners or inclined surfaces. In one case,
the flow remains attached for a longer distance before eventually separating. In another case, separation occurs earlier and produces a more irregular wake. Smoke or chemical visualization techniques are used to trace the flow paths. These results confirm the role of initial conditions and pressure gradients on flow stability.
Laminar versus turbulent boundary layers. Laminar boundary layer separates very easily under an adverse pressure gradient. In contrast, a turbulent boundary layer has higher momentum near the wall and therefore resists separation more effectively. Visualization using titanium tetrachloride shows a clear difference in wake patterns. In laminar flow, the separation line appears clean and well-defined. In turbulent flow, the wake structure is more irregular, but the flow remains attached for a longer distance.
Check your understanding. Number 29. Why does the turbulent boundary layer resist separation better than the laminar boundary layer under adverse pressure gradients? B. Turbulent boundary layers have higher momentum near the wall, allowing them to overcome adverse pressure gradients more effectively. Explanation of why other answers are wrong. A. Turbulent boundary layers are thinner and less affected by pressure gradients than laminar ones. Incorrect, because turbulent boundary layers are generally thicker than laminar ones, and their resistance to separation is due to higher near-wall momentum, not thickness. C. Turbulent boundary layers generate less drag, which prevents separation in adverse pressure gradients. Incorrect, because turbulent boundary layers typically produce more drag, but their higher momentum helps resist separation. D. Turbulent boundary layers are unaffected by pressure gradients, unlike laminar ones. Incorrect, because turbulent boundary layers are affected by pressure gradients. They just resist separation better due to their higher energy near the wall. Slide 166. Slide ini dilewati karena berisi soal evaluasi dan bukan bagian dari alur penjelasan konsep. Fokus pembahasan tetap pada pengembangan teori dan visualisasi fenomena lapisan batas. Dengan mengabaikan bagian ini, kontinuitas penjelasan tetap terjaga. Materi inti tidak bergantung pada pertanyaan ini. Alur logika tetap utuh untuk memahami langkah-langkah berikutnya.
Turbulent flow over a bump. This figure shows that turbulent flow can maintain attachment better when passing over a bump. Even though an adverse pressure gradient exists on the rear side, separation can be delayed or even avoided. The streamlines appear more stable compared to the laminar case. This is due to stronger momentum mixing inside the turbulent boundary layer. This concept is very important in aerodynamic and hydrodynamic design. Turbulent flow over a bump. A turbulent boundary layer has a better ability to resist adverse pressure gradients. The outer flow remains relatively stable and follows the surface contour. Compared to laminar flow, the attachment in the rear region of the bump is much better. CFD simulations provide detailed insight into this flow structure. In practice, turbulence is often used deliberately to delay separation. Momentum integral control volume. The control volume is defined to include both the boundary layer region and the free stream above it. The momentum analysis considers pressure forces on the left and right faces and the shear force at the wall. The change in momentum inside this volume must balance these forces. This approach allows the derivation of an integral equation without solving the full Navier Stokes equations. This concept is the basis of the Kármán integral equation.
Mass flow balance in control volume. The mass balance states that the mass flow rate entering the control volume must equal the mass flow rate leaving it. The growth of the boundary layer changes the mass flow distribution between the near wall region and the free stream. The outflow occurs not only through the right face, but also through the top of the control volume. This principle comes directly from the conservation of mass. Without satisfying mass balance, the momentum analysis would not be consistent.
Reverse product rule in momentum equation. The product rule of differentiation is reversed to facilitate the separation of terms in the derivation of the momentum integral equation. This approach allows the velocity integrals and spatial variations to be handled systematically. With this manipulation, the equation becomes easier to relate to physical boundary layer quantities. This step is mathematical in nature, but crucial to obtain the final form of the Kármán equation. Without this technique, the derivation process would be much more complicated and impractical.
Check your understanding. Number 30. The product rule is reversed to facilitate terms separation in the momentum integral derivation.
Integration for Kármán equation. The application of the Kármán equation requires integration of a known or assumed velocity profile. The accuracy of this integration process strongly determines the correctness of the computed shear stress and momentum change. Each choice of velocity profile will produce different quantitative results. Therefore, the assumed profile must be physically reasonable. This step connects the theory with a practical approach to boundary layer analysis. Flow over thin, flat plate. The flow over a thin, flat plate is used as a fundamental model to study boundary layer development. The simple geometry allows the focus to be placed on viscous effects and the Reynolds number. The analysis is performed for a wide range of flow conditions, from low to high Reynolds numbers. From this case, the growth of the boundary layer along the flow direction can be observed. This model becomes a primary reference in many engineering applications. CFD visualization of flow over flat plate structure. The numerical visualization shows how the flow pattern changes as the Reynolds number increases. At low Reynolds numbers, the flow appears almost uniform without a clearly defined boundary layer structure. As the Reynolds number increases, the velocity gradient near the plate becomes much steeper. The streamlines start to crowd near the wall due to viscous effects. These results provide a strong qualitative picture of boundary layer development.
CFD analysis of flat plate flow. At low Reynolds numbers, the flow remains nearly uniform and the boundary layer is not yet significantly developed. As the Reynolds number increases, a boundary layer begins to form and grow along the plate. The velocity profiles become steeper near the surface. The streamlines near the wall become more crowded, indicating strong viscous effects. The entire simulation assumes steady, incompressible, and laminar flow.
Boundary layer thickness calculation. The thickness of a laminar boundary layer can be calculated as a function of the Reynolds number and the position along the plate. This computed result can be directly compared with the velocity profiles obtained from CFD simulations. The agreement between them shows that the theoretical approach is reasonably accurate. In practice, this calculation is used to estimate the region influenced by viscosity. A smaller thickness indicates a flow increasingly dominated by inertia effects. Velocity profile family. These curves shows how the velocity profile changes for different Reynolds numbers. The vertical distance is normalized so that all profiles can be compared in a single graph. It is clearly seen that as the Reynolds number increases, the boundary layer becomes thinner. The curve shapes also show changes in the velocity gradient near the wall. This representation helps in understanding the quantitative evolution of the flow structure. Velocity profiles in laminar flow. The velocity profiles are strongly influenced by the Reynolds number. With higher Reynolds numbers, the boundary layer becomes thinner and the velocity gradient becomes steeper. At moderate Reynolds numbers, a slight velocity overshoot may appear before disappearing at extreme conditions. The profile shape gradually becomes flatter in the outer flow region.
CFD results make it easier to visualize these changes in detail.
Check your understanding number 31. How does the boundary layer thickness change with increasing Reynolds numbers? C. The boundary layer becomes thinner, highlighting streamlined effects and reduced flow separation. Explanation of why other answers are wrong. A. The boundary layer becomes thicker, emphasizing the effects of turbulence at higher Reynolds numbers. Incorrect, because higher Reynolds numbers typically result in thinner boundary layers, not thicker ones, as the flow becomes more streamlined. B. The boundary layer thickness remains constant, as Reynolds number does not influence flow profiles. Incorrect, because the Reynolds number directly affects the boundary layer, causing variations in thickness and flow behavior. D. The boundary layer fluctuates in thickness, depending on the presence of velocity overshoot. Incorrect, because while velocity overshoot can occur, it does not cause significant fluctuations in boundary layer thickness. The trend is towards thinning with increasing Reynolds numbers.
References. This section lists the main sources of figures and materials used in the discussion. The reference comes from the standard textbook by Eunice A. Chengel and John M. Chimbala on fluid mechanics. This book is an important reference because it provides a balanced conceptual and mathematical explanation. Using this source ensures that the explanations are consistent with international literature. This reference can also be used for further in-depth study of the topic.